Hey everybody! So, take a look at my screen. We have MIDI working. So, musical instrument digital interface works with my Korg X3 keyboard. We got that covered. So let's move on to some more audio goodies. So, here's what I'm thinking. Let's tackle pitch detection now. You saw this in the show and tell. It was pretty cool. Let's actually make this happen. Now, I want to start with an HTML file. Demo, right? We want to make a demo, so it's going to be called pitch detection.html. And then let's give it a title, pitch detection. All right, cool. And so the next thing I'm going to do, obviously, I'm going to add a JavaScript file. There's a lot of code here, so we'll add it in a separate JavaScript file. So that'll be our pitch detection demo.js. All right, so empty file here. Let's go back to pitch detection.html. And I'm gonna add an ES6 import, a script tag that lets us import stuff. I am making a class called Vox Controller, voice controller. So we'll need to add that to our pitch detection demo class. Export class Vox Controller. All right, so we got the class going here. Now hold up, before we do anything, I want to acknowledge that I'm stealing a lot of code here. I'm going to copy and paste some attributions here at the top of my class. Now this all comes from that blog post I mentioned in the show and tell. Alex wrote a great write-up and I'm stealing a lot of his code and kind of refactoring it. So I'm noting that. And then furthermore, this autocorrelate functionality comes from this Chris Wilson GitHub repo for pitch detection. So the most obvious thing to start with here in this class is to add some microphone behavior. So first we want to toggle this microphone. So when it is active, we're going to set this static active to true. And we're going to use that and say, if it's active, stop the microphone. If it's not active, we'll start the microphone. Basic toggle functionality here. And of course, when we want to stop the microphone, we'll want to set active to false, and we're going to close this audio context. We're going to be using the web audio API here, and audio context is one of those things we're going to need. So let's add that to our static properties as well. And keep in mind, this is a class, but it's not going to be instance-based right now. It's all static. It's all kind of singleton. And the reason is I only have one microphone. You're only going to see one instance of this globally in this project because we're just getting it from our one source. So this is why we can be static here. Just like using web MIDI, there's only one MIDI source coming into your computer, so not instance-based is kind of a global thing we can use. The other thing I want to do on stopping my microphone is to update our listeners. Now, I don't have any listeners yet, so let's add those. They'll be Kluge listeners, just like the MIDI example we did, where we're gonna keep an array of callbacks, and when we want to fire off those callbacks, go through our listeners and fire off what's active now, what the current node is. The most important thing of stopping the microphone, I think, is letting folks know through these listeners that we're turning it off. So we're gonna send that active state. And of course, a small thing, we need to be able to add listeners here as well. So there we go. We got everything in place, I think, the audio context, the listeners. So that's stop microphone. Now, start microphone, of course, is the interesting thing because we're going to start listening through our microphone. We're going to set a few things here. We're going to create a new audio context. And again, this is the web audio API. What we can do here also is create an analyzer. So this analyzer, this is what's going to peek into our audio and let us look at the fast Fourier transform of the audio. So this is how we kind of run the pitch detection, and honestly kind of how we're going to draw on canvas what we're seeing with the audio as well. So we got our audio context going, we got an analyzer, we're setting some limits on this analyzer as well. Like what do we want to listen to? How high is the volume? How low is the volume? Cut off everything in the middle. And then some smoothing, how smooth do you want this fast Fourier transform? So again, I kind of just stole these settings, but they work super well. And to get this microphone started, of course, we have to get user media. And this gets a little tricky because If you're on localhost, everything's going to work just fine. If you're not, I think you have to be over a secure context to use this. So HTTPS if you're on anything except for localhost. Them's the rules. This is how we have to get user media over this secure context. So this is why we have to have a couple checks here. One, when just audio is not allowed, maybe your hardware doesn't support it, who knows. But other than that, we're getting the user media and we're saying audio is true because that's all we really need here. So once that promise resolves, we're gonna have a stream, a microphone stream. So let's fill in this promise resolve with some stuff. So what we're gonna add in here is a few lines of code. So we're gonna start initializing the source nodes. So if you've ever worked with a web audio API, you know that you need some audio sources. You can have multiple going to the same destination, but we need a source. And this source we're gonna have is created from our media stream, from this media stream right here. And we're saving this to a source property. So let's add that property in right here, this static property. We'll pop that property right here. So now it's on our class and we can have that saved for us. And then we're gonna connect our analyzer to that source so we can get the fast Fourier transform of that source. And then we're gonna, go through all our listeners that we've added. Maybe we haven't added any, maybe we have. If we have any listeners, we're just gonna fire off the current status of things. The most important thing here is whether this class, this voice controller, is active right now. And you wanna listen to that for when you know the microphone is starting up. So it's a good thing to call out to the outside world to say, hey, we're ready. We're ready for audio. And then this final line right here, we're just gonna launch into doing some note detection. So this function is not here yet, but let's add it in here. So what are we looking at here? We are looking at a very short function. The reason it's short is because we want to keep running it over and over and over again. So this is just the very first step in our note detection journey. So what happens here is detect. We don't want to just call it once. We want to do continual detection. And I think I want to do it really fast. So as fast as the frame rate that our browser lets you. So we're going to use request animation frame. So every request animation frame, we're going to say, if we're still active, then run this same function again. So detect. So while this function is queued up waiting for that next frame, we're actually going to do the note detection right here. So we need note detect. We need a function. Now this detect note, this is where I really steal a lot of code. I probably couldn't walk you through a lot of this, but here it is, detect note. So we're starting off with some audio buffers going through. We have some variables here, smoothing threshold, smoothing count threshold that we're setting. And these, again, I need to add these variables to our class, so I'm gonna do that right now. Now, I think these are the last of the properties I need to add to this class. Just a bunch of stuff, depending on your current situation, whether, there's a smoothing value. And honestly, I have extra code in here because we can make smoothing basic, or a few other options right here, none, basic, or very. So this smoothing value can control how smooth the fast Fourier transform is analyzed and have some different results based on that. But honestly, I'm just hard coding basic right now because it seems to work pretty well. When I was using the demo from Alex, basic seemed to work pretty well, so I'm running with that. But jumping back to the top here, there is this autocorrelate function. This is the super mathy stuff. So let's copy and paste that function in as well. Now with that pasted in, I'm gonna tell you that I am not gonna explain this because I don't really think I understand. I have to sit down with it, do a lot of pondering about life and math and everything like that. But again, this all comes from Alex Ellis's blog post, Detecting Pitch with the Web Audio API to Autocorrelation. And if you want to know how all the math stuff works, lots of diagrams, lots of great explanation here. So this is the autocorrelate stuff that I just put in. Now with autocorrelate put in, you'll notice this next thing is note from pitch. Now that it's already autocorrelated, now that all the mathy goodness has been done, hey, I need a semicolon here. I don't want to be I don't want to be untidy with my JavaScript code, but once we have that autocorrelate value, we're going to need to autocorrelate that to different notes. So what I'm going to do is note from pitch. I'm going to add this one function right here. So you pass in the frequency, and what it does is it gives you a note number. Yeah, it'll return that note number. And then with that note number, we can take this string of notes we have right here, starting at C, working itself all the way up through just a single octave. We can correlate that number, that note number, with the item from the array. And so once we've matched that note that we found to this array, we've given it a name. So this note could be a G sharp, it could be a B, it could be a C, whatever. So that's what this note is right here. And now I'm scrolling past this update note, but I'll get to that. What I want to focus on now is the note similar enough to, the last note? So basically, if you're a touch higher than the last note, but it's still a C, you kind of just want to capture that and say, well, it's the same thing. Don't send any updates that we've updated our note because, yeah, I'm just singing like a hair higher than the previous C I did. Then yeah, nothing's changed. But if I change from a C to a D or a D sharp, then we've obviously changed something. So we got to figure out if this note is similar enough, and that this is how we're going to do it. And it really comes down to this smoothing threshold we have here. Again, lots of math that I'm not going to necessarily explain. I'm just giving you the vibe of how this works. So yeah, and lastly, we got down to an update note again. So up here, if the autocorrelate value returns nothing, then we're obviously not singing a note. So we're going to update our note and tell the world you are not singing anything worthwhile. Harsh criticism, I know, but there it is. So we need to update our note to nothing. But if we made it all the way down here, we actually have a note that we have to update, everybody listening with. So we're gonna call update note here, and this is one of the last functions we're gonna add here. So what this update note basically does here is it's just taking the incoming note and kind of comparing to the last note. The note itself is stored as something like C4, where you have the note and then the octave it has as well. We're only listening to one octave here, so we're calling everything the fourth octave, just to fulfill like some of the API in the application, because that application does use octave as well. But again, here we're just saying everything is the fourth octave, but we do want to report that it is a C4 or a D sharp 4. So we're kind of doing some string manipulation to parse those out. So what we're doing is telling everybody what the last note was and what the new note is, all in the same callback here for whoever's registered as a listener. And yes, I did forget to add one more property here. It's just the octave. So let's pop that in. And again, I said that octave would be 4 all the time. So there it is. Now, I think we're ready to demo this. It's not entirely here yet, but we have enough here that we can start making some things work. So let's add some HTML markup here. So we're going to start with a button, and then a span tag to display what note we're singing. And that button is going to let us start the microphone, just like it says. So yeah, start microphone. I know we're tempted to like load this up and press the button. One more thing though, we actually need to listen, add some callbacks to the listeners here. So once the note is detected, it can actually come back and tell us what that note is. So here we go. We have if the note down, which means I'm singing, and that's kind of like a down on the keyboard. You press it down. When you start singing that note, when it's down, it's going to set the inner text of the element note singing. So this guy right here, it's going to fill it in with like a C sharp or a D or whatever. So I think we're ready to go. So let's start this singing. So again, no web dev server required. We're just using ES modules, normal, simple HTTP server here. So let's start this up. Moment of truth. So we're gonna start this microphone. it's already giving some, because I'm just talking, it's bouncing all over the place. But you can see this indicator right here. It's saying it's listening to audio. Let's sing a solid pitch and see what we can get. Yeah, I sang a few notes. I don't know what I'm singing until I sing it, but that's not the only thing we can do right now. We want to be able to see some indication that the microphone is working, kind of a nice visual feedback to our users. So let's add that in right now. So I'm going to add in this canvas here, just a predefined, width of 500, height of 250, and then we're going to set up this canvas when we start the microphone. If you've ever worked with the canvas, you set it up, you get the 2D context. Unless you're working with 3D, then it's a WebGL context. But here we're using a 2D context because we're not using 3D. And then we're going to want to render our visualization. So I'm going to call this render visualization function with our context and with the canvas. Now again, I'm going to use a request animation frame here as well because we want it to keep visualizing. So we want to start this visualization by calling render visualization, but it's going to request animation frame, call render visualization again and again and again every time this function is called. So it's going to keep going. And then we want to call into our voice controller to visualize. We haven't added this function yet, so let's do that. So I guess I'll pop this visualization function about right here, above all the detection stuff that I don't really know how it works. So visualize, we're taking in a 2D context, the canvas width and the canvas height, and we're using the analyzer, the FFT analyzer of the source audio, and we're, parsing that out and using some drawing tools provided by the canvas context and doing just a bunch of drawing. And that's it. I mean, we're looping through our audio buffer here, grabbing data, grabbing samples in a current time snapshot, and just drawing lines. And that's pretty much it. But yeah, this should give us a good real-time canvas FFT drawer. So I think this is it. So again, let's jump back to our HTML file and load this up, and fingers crossed it's gonna work. Now you'll notice this button is a little further down the page, and that's because the canvas is about right here. So let's start our microphone. Yeah, right away, look at this. You can see the visualizer doing its thing, it's rendering. So can I hit a C again? I don't know, let's try this. Well, that was a G, 5 notes off, but I hit something. So yeah, this is all working. So yeah, this visualization tool plus the note detection, this will be amazing to have in our final audio application. So let's do one more audio goodie in the next segment. So yeah, we're gonna cover Tone.js next. I think that's gonna be fun. So stick around.